Okay, let's continue on transformer. So on Wednesday, we first talked about ideal transformer. And then we also discussed how to model some practical consideration compared to real transformer. So for ideal transformer, we only just need to know this equation. So the voltage on the primary side divided by the voltage on the secondary side will be equal to the ratio of the turns of the two windings. Based on the conservation of energy, so the current on the secondary side divided by the primary side will also be the ratio. So that's ideal transformer. But since for practical transformer, there will be some factors we need to model. First will be on both sides, there will be some resistance in the winding. So we need to model the resistance on both sides, R1 and R2. And also there could be some leakage flux. So which means those flux will not stay inside of inside of the two legs. So that one will create some voltage drop. That can be modeled by the reactance, S1 and S2. And also to build up the magnetic field, you do need to give the transformer a little current before the transformer can function normally. So that current will contribute one part to build up the magnetic field, and the other component will generate some loss due to the eddy current. So that also need to be modeled. So finally, we have two impedances on both sides, modeling the imperfection of the wires, the windings, and also we have two shunt branches, one resistance and the other reactance to model the factors with the iron cores. But once we have this circuit, we can definitely use the Kirchhoff voltage law and current law to do the calculation, to calculate power on either side of the transformer. But it's not very convenient because we really don't want to have this one separating the primary side and secondary side circuit. We want to have a unified circuit, which is similar to the equivalent circuit of a generator. With some internal voltage, which could be the primary voltage, and some type of resistance or reactance to model the imperfection of the transformer. So in the next slide, so we introduce there could be a transformation. So we can transform everything from a secondary side to the primary side. Like if there's any impedance, any current, any voltage, we just simply move over to the primary side. It just regard the ideal transformer part not existing at all. We need to divide the current by the ratio, multiply voltage by ratio, multiply impedance by ratio square. That transformation from secondary to primary side. We can also do similar transformation from primary side to the secondary side. So any branch, any current or voltage can be simply moved over to the secondary side, and you just need to multiply current by A, divide voltage by A, and divide impedance by A square. So either way will give you the same topology of the circuit. So you just simply move the ideal transformer on one side of the entire circuit. But this circuit is still very complex. We still want to further simplify this circuit. Then in the following slides, there's two ways to further simplify the circuit. For instance, we can move this shunt branch to one side to be directly connected to the source. So by doing so, we can merge the two series impedance by a single impedance. If the primary side has very high voltage and usually moving those two shunt branches doesn't cause much error. So that's first thing we can do. So then we can merge the impedances of two windings by a single impedance. But we still don't like this shunt branch. We can just simply ignore it. If the transformer is built very well, we can ignore the initial current to build out a magnetic field, and also if the ID current can be limited by designing the transformer by material, we can ignore both of them. So that will create very simple equivalent circuit with basically just single impedance. So this structure has been very similar to the structure of any source, like a generator, right? In the generator, we on the source side we have a EMF, a excitation voltage, and which is connected to a signal reactance and also the armature resistance. Then it can power the load of the external system. But so now we have generated structure very similar to the equivalent generator circuit. But the only thing different here is you do need to decide on which side you want to transform, because you can either transfer everything to the secondary side, and right now the voltage will be taking the voltage on the secondary side voltage. If you move everything to the primary side, all the voltage will be based on the primary side voltage. You do need to keep that in mind. But later when we introduce the per unit system, so that problem can be resolved. We don't need to worry about what voltage we need to consider, because per unit system will take values which is similar to percentage of their nominal value or rated value. So you just define the base, and then you only do the calculation based on the per unit value. So no matter which side you're going to transfer for the transformer, you'll get the same circuit, same result in per unit. Okay, next I want to quickly talk about the efficiency of a transformer. Because it's a not ideal transformer, so efficiency will be lower than 100%. So we need to model the power loss of the transformer. So for any part of the transformer with some resistance, or that can be modeled by resistance, that will cause some power loss. So let's assume the secondary side winding. So the sub-2 just indicate the quantities about the secondary winding. Assume the secondary side is operated at the rated condition. Apparent power will be 3 times of secondary voltage and secondary multiplied by secondary current. They're both rated value. And also, if we know the power factor, and the actual load is actually the rated current multiplied by a fraction. So we use n. N is less than 1. If you are operating the transformer at 50% of load, so n will be equal to 50%. So actual power will be apparent power multiplied by power factor, then multiplied by this fraction. So that will be the actual power. So if the transformer operated at rated condition, so there will be a copper loss due to the resistance in the two windings. So if it's operated at rated currents, so this will be the total copper loss. So this RE2 is actually the total resistance if we transform everything to the secondary side, because the sub E just indicate the total resistance, and 2 indicate it's after transformation to the secondary side. If you transform everything to the primary side, that will be RE1. So under the current condition with a fraction of the full power, so that will be the same resistance but multiplied by the actual current square. So that will be N square times the rated copper loss. And the next loss will be the iron loss. That is caused by the eddy current in the air. So that one doesn't depend on current, that depends on voltage, because that shunt branch is almost directly connected to the source voltage. So for transformer, there's not much room we can change the voltage. Even there's some room we can use the transformer to control voltage, as we discussed in the later slides. But usually the voltage can vary in a very narrow range. So it have to be close to the rated voltage levels. But current can largely change from maybe 0 to a fully loaded current. So such as the error loss doesn't change a lot. It will be roughly the same value. So efficiency will be the actual power divided by the total power from the source. So the total power from the source definitely need to provide the output power, and also need to compensate the loss of the copper and also the iron. Okay, so that will be this is the output power. So you see the N just indicate the loading condition, and this is still the output power, and this is copper loss and iron loss. If you do some simplification, you will have this formula. So there's an example 3.4 showing some calculation based on this formula. If you want to figure out maybe the highest efficiency the transformer can operate, you want to maximize this expression, so which is equivalent to minimize the denominator. So if you minimize denominator, since the parent power and power factor, if they don't change, the only thing to change will be N, right? So N appear in the last two items, so which is multiplying the copper loss and dividing the iron loss. So for such case, if you want to find the minimal value, which is basically equal to those two items to be same, oh, you just like this is function of N. You can just calculate derivative of the function with respect to N. But conclusion usually will be those two items to be equal. That will give you the minimal denominator, which is the maximal efficiency. Okay, so you can take a look at that example for more details. Okay, next we want to introduce a concept, voltage regulation. The voltage regulation is some index evaluating the quality of a source. Okay, so if it's an ideal source, it definitely need to have internal voltage, which is the source voltage, and you can open the circuit of the source or connect the source to any circuit. The circuit can have a high current, low current, but for ideal source, we usually expect the voltage doesn't change with the condition, right? That's a perfect source. So which is like you buy a battery, you can go a AA or AAA battery. It just tell you how much volt you have. So you just connect to a circuit. For a very new battery, the voltage will be about the same based on the value shown on the battery. But when you operate for a long time, so the resistance inside the battery will increase. Finally, the voltage you get become lower and lower. Finally, you just have to replace the battery. So that's similar to also any AC source in AC power system. So we do need such a index to evaluate the quality of a source. So the voltage regulation is defined to be a fraction. So denominator will be a rated voltage. Okay, that's the voltage this source are supposed to operate at, and the numerator will be the one which is called no load voltage. No load voltage, which means just open the circuit, and minus the rated voltage. Okay, so those two values are supposed to be same, right? For ideal source. For the ideal source, it doesn't matter how much a load is, the voltage should be about the same. So for the ideal source, the numerator should be around 0. So which means 0 voltage regulation means ideal source. But if the no load voltage and the rated voltage are very different, in order to hit, so if this source is not good enough, in order to operate at the rated voltage, I have to create some internal source to have much higher voltage, which means the quality is bad. So for generator, that internal voltage is excitation voltage E. And the external voltage, when it connect to circuit, will be the terminal voltage, okay, when we carry a current. So the relationship can be taught from here. So the E is the internal voltage and V is the terminal voltage. And the voltage difference is generated by this internal impedance. So if this internal impedance can be ignored, E basically is equal to V. But depending on how the generator is designed, there will be some internal impedance. For instance, if you can reduce the leakage flux, that can reduce the synchronous reactance. If you use better material to reduce the loss of the generator, that can decrease the RA, right? So that will reduce the impedance. So when you reduce that internal impedance, that make the terminal voltage be close to the E inside of the source. For transformer, we can also use similar concept to evaluate the quality of a transformer to behave as a source. But we need to utilize the equivalent circuit referred to one side. So for transformer, based on original definition, because we're going to use the secondary side voltage to connect to a load, so that secondary side voltage at rated value will be the V rated, and the source voltage will be the secondary side voltage when you open the circuit. Right, that's the source of the voltage and divided by the rated voltage. That's the original definition. But then we need to transform to either the primary side or secondary side. If we transform to secondary side, so the second at the V2 rated will basically just V2, and the no load voltage will be the source voltage transformed to the secondary side. So you see, we put V1, which means primary voltage, but there are also a prime here, which means after the transformation. So the equation will be this one. So here, this is indicate the total impedance after we transfer everything to the secondary side, because we have the sub E and the sub 2 that indicate that total impedance transfer to the secondary side. And the source voltage is actually the primary side voltage source transformed to the secondary side. Okay, so we're going to use this equation to calculate the voltage regulation factor. So if we transfer everything to the primary side, so the source voltage will be same as the actual source voltage at high voltage if this is like a step down transformer. But rated voltage which connects to the load will be the load voltage transformed to the primary side, because here we have sub 2 indicate that's a secondary voltage, single prime indicated transform to the primary side. Then we are going to use this circuit, this equation to do the calculation. There will be some homework question for you to practice on how to calculate voltage regulation. So keep in mind, the voltage regulation equals 0 means ideal source. Okay. So the bigger, if we're talking about the positive voltage regulation, which means the no load voltage is higher than the low voltage, which is like, if we talk about the source voltage for generator to be higher than the terminal voltage. So when we increase voltage regulation, which means the E should be higher, right? So the quality will be worse. Okay, so the higher the voltage regulation, the worse the quality of the source. So which means the gap between the voltage should be increased, right? In order to make because for generator, that's this should be this formula, right? Divided by V. But for generator, it could happen, the E is lower than V in what condition? So which means voltage regulation can be negative. Remember in the phasor diagram, we work on this case. When the power factor is leading, the E can be shorter than V. So for that case, the voltage regulation can be negative. Okay, so voltage regulation can be positive or negative depending on what power factors you're operating the source. But if voltage regulation is 0, which means like ideal source, close to ideal source. Any question? All right, so next we move to a 3-phase transformer. We just quickly go through some conclusion you're probably already familiar with when you took a 325. So there are basically 4 combination of connections because you need to decide either delta or the Y connection on either side. And considering both primary and secondary windings in 3 phases, so there will be a Y to Y, a delta to delta, Y to delta, delta to Y. Okay. So for Y to Y, delta delta, that's simpler. Those are similar connections because their high voltage, low voltage ratio is same for line and phase voltage. So you either take both line voltage or both phase voltage to calculate the ratio. So the ratio on each phase is also exactly same of the ratio for any other phase or for any either line voltage or phase voltage. But unfortunately, actually the Y to Y is actually the easiest one to do any calculation. But Y to Y is really used in practice because it has a lot of third order harmonic issues. I'll talk about that shortly. And Y to delta connection and delta Y connection are more common connections in actual transformers. So Y to delta connection can be easily used as a step-down transformer because even the primary and the secondary side for each phase, the transformer design is exactly the same. Basically, you just use the 1-to-1 ratio for single-phase transformer. You just connect 3 such transformers to behave as a Y to delta connection. That already step down the voltage because on the primary side, you use line-to-line voltage. On the secondary side, you only use a line-to-neutral voltage or single-phase voltage. So you already generate the ratio, which is 1.73. Even the number of turns on both sides are identical, same. So that's very easily to consider Y to delta as step-down transformer. Similarly, delta to Y will be commonly used as a step-up transformer. So what I'm talking is, so if this one and that, maybe I need to draw the other one. Okay, if those two come from the same 2-leg transformer or single-phase transformer, and with a ratio 1-to-1, and the line-to-line voltage is already 1.73 to 1, right? So that saves you cost. If you really want to build step-down transformer, you don't want to make this guy to be a step-down transformer because when the ratio for each phase being 1-to-1, and the ratio is 1 to 1.73. So if you want to make the primary side to have higher voltage, you need to have more turns. So that's not the efficient way to design the transformer. So you want to use this one as step-down transformer, and this one naturally generate 1 to 1.73 as step-up transformer. Okay, if you want to make this ratio to bigger, so you just need to multiply by any, just increase additional ratio. So that will give you more step-down transformation. Okay, Y connection has a neutral for grounding and lower insulation costs, but the third order harmonic problem. The third order harmonic problem really because the third order harmonic for voltage current, they become in phase. Okay, they will add on to each other. For diode connection, the drawback is there's no neutral point. So if there's any fault, sometimes the neutral current become non-zero. You do need to have that neutral wire to connect the short circuit to the ground or to somewhere else for the protection. But if you use diode connection everywhere, you don't have that. There's no place you can add that neutral wire. So you need to. The better idea is the transformer will split the entire network into section by section, depending on voltage level. So in each section, it's better to have at least one Y connection. Okay, so it can be delta to Y and Y to delta. Even then, if you have delta to delta, but next one is better to use Y. So any section you need to have at least one Y. That will give the simplest design to still keep the neutral wire for each section. Another benefit of using diode connection is it's very convenient to do maintenance. So you can just simulate do the maintenance for each leg. When you open, you disconnect this leg between C and B, the other two legs can still operate as three-phase transformer, but the rating will decrease to about 87% of the original rating. It's not too bad. As long as it's not operated at full loaded condition, you can do maintenance for a single leg. The calculation is not hard. Have you did the calculation for Y is around 87% in 325? You can try. It's very simple. I don't go through that one in this class, but basically, you calculate the rating. For example, with the delta, the full delta. Okay, for full delta, the line current will be the sum of the two phase currents. But once you open the one phase, so that phase current will become the line current. So which means you decrease the line current rating to the rating of the phase current. So that will make your calculation slightly different for the diode connection. So that's why the rating will be decreased. But that is very easy calculation. So how are we going to do calculation for a three-phase transformer? So the approach is to replace any delta connection by equivalent Y connection. So once you replace every delta by Y, you only pick a single phase of the Y. Then you just do the calculation for single phase AC circuit. Because this course assumes steady state conditions, so we balance a three-phase balance will be assumption for any question, any problem. So we can definitely just assume calculating one phase, we can duplicate the result also for other two phases. To do that, we just need to use this transformation for any voltage, for any impedance. If it's a phase of the diode connection divided by 3, we'll get impedance of the one phase in the Y connection. And all voltages will be aligned to neutral voltage. So if it's original diode connection, you need to calculate the line to neutral voltage by divide the voltage by 1.73. Okay. Let's quickly talk about this third order harmonic problem with three-phase transformer. So assume we have delta connected balanced loads. So which means the three load impedances are exactly the same. And now we assume because the load has some, when we power the load, the current will be distorted somehow to rectangular wave or maybe square wave. Square wave means it will not be perfectly sinusoid. The current is not perfectly sinusoid waveform. It's not very smooth. But definitely you can do the Fourier transform. If you do the Fourier transform, how many harmonics do we have for the square wave? Do we know? If it's a rectangular or square wave, which means each half cycle, so they're basically symmetric, okay, perfect symmetric. So if we do the Fourier transform, you are going to generate, definitely you have the omega, that's a fundamental frequency, right? And next one will be third, fifth, seven, nine, so you can continue. But you only have odd number, odd order harmonic. You don't have even harmonic. Because your original waveform is symmetric. So only odd order harmonic will guarantee the symmetry. Does everyone follow? Right? So just give you a simple example, because if this is a square wave, so this is fundamental, right? Then you have a third order harmonic. Then you have maybe ninth order harmonic. But you won't be able to have even order harmonic. Even order harmonic means there will be something like this one. That will be will have the frequency twice of the fundamental frequency, because this green one will change the final shape. The final shape will be distorted, not symmetric. So that can make that will make the shape not symmetric. Let me use. Let's change the color. That will make this one not square. Will be somehow like non-symmetric. Okay, but anyway, let's just assume this simple case, like a square wave. So we'll have only odd number harmonic. So I color the third order harmonics, such as the third, the next, or the next one will be 11, 12. 12 is not there. The next one will be which one? 15th, right? But this too high, so usually we can ignore. So you don't have to consider very high order harmonic, because the higher the order, the smaller the magnitude. So you can stop somewhere. So usually 5th or 7th should be enough. Okay, third order harmonic is still significant. So for instance, this is like distorted waveform. It's already similar to the square wave. It's still far from square wave, but this distorted waveform is made up by considering fundamental and the third order harmonic. For fundamental harmonic, the three phases will have 120-degree difference. But come to the third order harmonic, they have no phase difference. Why? Because the original red wave is IAB, which is the current from phase A to phase B. And the IBC will be lagging IAB by 120 degrees. And third order harmonic is trying to, for each half wave, we will generate 3 half waves. So because the frequency is 3 times, so the third order harmonic current for the phase from B to C will be this one. You see that is exactly aligned with the third order harmonic of IAB. So further, if you do that for ICA, that's also same. Basically, the third order harmonic currents of 3 phases add on to each other. Which is not the best thing to this delta connected circuit, because if the third order harmonic of this IAB and ICA add to each other, which means it's fully trapped by the delta connection. It never escaped from the delta, right? Because this third harmonic is equal to that one. Based on the Kirchhoff current law, there's no third order harmonic on this line. So all third order harmonic fully trapped by the delta connection. So you won't be able to see the third order harmonic on the system, on the network. It only happened locally with the low. So that explains why we need a delta connection. So as I said, to have the neutral where it's better to have Y connection in each section. And if you do have distorted waveform and you need to trap the third order harmonic, it's better to have a delta connection also in that section. So that's why the delta Y, Y delta are more commonly used transformers. So next we need to talk about some calculations using the phasor diagrams. But a drawback of using Y to delta, delta to Y, although they have a neutral wear for the grounding current, and they also have the ability to trap the third order harmonic, but they will cause a 30-degree phase shifting between the primary and the secondary voltage. 30-degree phase shifting, which means the voltage on the primary side will not be in parallel with the voltage in the secondary side. They'll be pointing to a different direction. So that will make the ratio be complex number, not real. This is very different from the single phase transformer. According ASA, the American Standards Association, the windings are arranged such as the high voltage line voltage lead the low voltage line voltage by 30 degrees. Okay. So when you have either Y to delta Y connections to decide which is A on primary side, which is B on the secondary side, you just need to make sure the corresponding two windings will have the high voltage always lead the low voltage by 30 degrees, not the other way. Let's give you one example. Let's just consider Y to delta connection. Okay, so that's step down transformer. The Y will be a high voltage side and delta will be low voltage. And if we know phase to phase ratio is A. So this delta Y connection three-phase transformer is made by, you can consider 3 identical one-phase transformer. Okay, and for each phase, the phase-to-phase ratio is A. So now we connect them to a three-phase transformer. But one side become a Y, the other side become delta. So I draw this because I want to make each phase voltage to be as a reference. So on the x-axis. So the right arrow on the primary side, which is the line to neutral voltage, and the blue arrow on the delta connection is the phase voltage. So those two belong to the same. They actually couple each other. They belong to the same single phase transformer. So they will have ratio, which is A. Okay. So now we draw the phasor diagram. So to draw the phasor diagram for the high voltage side, we have a VAN, VBN, and VCM. So ABC here are all capitalized because they means the high voltage side. And so each VAN will be equal to the high voltage side phase voltage. So line voltage will be, for instance, if we draw the VAB, which will be the a phasor connecting starting from a VB to VA, right? So we utilize the triangle, so that will give you the VAB. That's line-to-line voltage. We know the line voltage and phase voltage. The difference will be this ratio, which is the root of 3, 1.73, and also there's a phase shift of 30 degrees. For the low voltage side, there will be delta connected. Each voltage will be it's line-to-line voltage, which is also equal to phase voltage. And the ratio N, ratio A is actually between each phase. So it will be the number of the high voltage side divided by number of the low voltage side. So we need to make sure to use the phase voltage. So here is just VA, capital AN to the VAB, lowercase VAB. Okay, so we just plug in the voltage and on the high voltage and low voltage side, so we can easily prove if we compare line-to-line ratio, so that will be a V capital AB divided by V lowercase ab. Okay, so if you plug in the formula, and you will get the ratio will be original ratio A multiplied by this phase shift, and also a factor of 1.73. So this number will be the new ratio for this Y to delta connection transformer, and so it is a complex number. Okay, so we'll need to deal with this complex number. Later in the power flow analysis section, so there will be some, we'll come back to this complex number again to discuss how this one can influence the calculation of complex power flow. All right, so I will further talk about the application of a transformer in real power system, focusing on the voltage control using transformer. We know for the real power flow, it can be calculated based on this formula. So if the angle is very small, so that sign angle difference can be replaced by angle difference. So basically, ID power depends on the angle difference on both sides. Okay, so if you can utilize the transformer to change the angle difference, you'll be able to control the active real power flow. Reactive power flow is calculated based on this formula if we ignore the loss. So this approximation is because of we ignore the loss. Okay, if you want to consider loss, that will be another more accurate formula you need to find from the previous section. So if the angle is very close, so the reactive power mainly depend on the voltage drop or voltage difference. So type changing transformer will utilize this idea to influence the reactive power flow, such as to control the voltage magnitude. Regulating transformer can either influence the voltage difference or change the angle difference to control both active and the reactive power. So this is one picture of the transmission level phase shifting transformer for 3 phases. Let's talk more about the type changing transformers for voltage control. So in practice, most of the transmission system level transformer and many distribution level transformer will have a tap by design. So they can change the turn ratios either online or offline. So some transformer, they can change the type positions, even it's operating, and some transformer have to be moved from the system, change the ratio, then connect back to the system. So let's use unload type changing transformer as one example. So this transformer can adjust turn ratio during the operation, which means they can participate in voltage control. They may even have built-in voltage sensing circuit for automatic type changing, which means you can design the negative feedback system. So by controlling the voltage on a certain point, so if that voltage lower, and that will send a signal to the transformer, and it will automatically move the tap up to increase the voltage or decrease voltage, depending on how the sensed voltage is lower or higher than the reference value. So let's use one unload type changing transformer as an example. So assume we have unload type changers at the low voltage side with 32 taps. 32 tap, which means there are 32 locations for you to move up and or down of the tap. And each time you move the tap, it will change the voltage by about 0.6%. So totally, you can expect to change the voltage by positive or negative 10%. So for instance, if the secondary side you have 100 kV, okay, so you can vary the voltage between 90 to 110 kV. Let's give you a real example. So this transformer is step-down transformer. So primary side connected to a 345 kV. The secondary is 138 kV, and it has the 32 taps. Okay. So you see, right now the tap is at the neutral point, so it doesn't move up or down. So the primary side, the source will provide 5 megawatt ready power to the transformer, and the transformer will take 3 of the 5 and give 2 megawatt to the load. Because transformer itself is still a relative load, not relative source, because it only have inductance. It doesn't have any capacitance, so it will consume some ready power and give 2 megawatt to the load. So if you want to increase the secondary voltage, so you can move up the tap. So by moving up the tap, you see the voltage will increase. So for this case, we move up by 5 taps. So 5, because the total number of taps is 32, which means on each side there will be 16. 5 divided by 16 multiplied by 10%, which is equal to 5 multiplied by 0.625%. That tells you if you move up by 5 positions, you are going to increase voltage by about 3%. By calculation, that is 142, about 142 kV. But actually, you only get 141 kV. Okay, slightly lower than the expected value. The reason is because you do the subtraction of the input ready and output ready power. So the 4 megawatt power is gone. That will be consumed by the transformer. So we will increase the tap position, that increase the loading of transformer. The transformer will consume 4 megawatt ready power more than the original condition. But definitely that still gave you the increased voltage, but it's not slightly lower than the expectation. So if you further move up by 16 tap, so you want to have 10% voltage increase, which is higher than 150 kV, but at the end you only get 146 kV because the difference now becomes 7 megawatt. So that's what happened in practice for transformer. Something you want to keep in mind, because transformer is, remembering the model only have resistance and reactance, right? So it doesn't generate any reactive power. It will be reactive load. Transformer itself is a reactive load. Although it can influence the reactive power, it basically just take reactive power from the primary side and give part of it to the secondary side. It's like a broker, right? It will charge more if you need more reactive power. So raising the secondary voltage through a type changing will increase its own reactive power consumption, which can cause some drop in the primary side voltage. Because if you check, the primary voltage will change from a 345 to 344 and 342. All right, so we will continue on Monday.